Today, we are going to make invisible power visible. We're going to take a deep dive into a custom-built IoT device, one that was designed to track every single watt of energy being used on a campus. So let's start with a simple question. How much energy does a building actually use? I mean, think about it. You see the lights, you feel the AC, right? But what about that massive, invisible river of electricity flowing through the walls all around us? It's totally hidden. Or is it? Well, this is the answer. This is the Campus Energy Monitor. It's a really cool IoT project that's all about tracking that hidden electrical flow in real time. The goal? To make every single watt, every volt, completely accountable. All right, so to really get how this works, we're going to follow the data on its journey. First, we'll check out the machine itself. Then we'll see how it actually senses the power, how it crunches the numbers, shoots them up to the cloud, and finally how it turns all that data into a beautiful dashboard. Okay, first things first. What is this machine really? Let's take a look at the anatomy of this energy monitor and see what makes it tick. So the whole system is really just a team of key players working together. You've got the ESP32, which is kind of like the brain. It does all the thinking and connects to Wi-Fi. Then there's the meter, this little guy called a PZEM004T, which does the actual measuring. The senses of the operation, that's the CT clamp, which safely clips right onto a wire. And once the data is collected, it gets stored in the database, which is ThinkSpeak, and finally displayed on the dashboard, which is Grafana. Pretty cool, right? And here they are. Let's get a closer look at that core duo. On the left, you've got the ESP32. That's the project's powerful, connected brain. And on the right, you see the PZEM004T. That's the super precise meter that does all the heavy lifting, measuring that electrical flow. Okay, but how does the system actually sense the electricity? I mean, that's the big question, right? And more importantly, how in the world do you measure high voltage without, touching a live wire? That seems kind of important. The secret here, the real magic, is something called non-invasive sensing. It's exactly what it sounds like, a way to measure something without actually touching it directly. In our case, it means we can measure all that electrical current without ever having to cut a single wire. It's just ingenious, and best of all, it's incredibly safe. And you know what's crazy? The whole process is so simple. It's just 3 steps. Step 1, open up the split-core CT clamp. Step 2, clip it right around a single phase wire. Step 3, close it. And that's it. You're done. It's now measuring the current just by picking up on the magnetic field that the electricity creates. No fuss, no danger. And you can see that awesome split-core design right here. That little hinge, that's the whole key. It's what lets you safely snap the sensor onto a live, high-power cable, all without shutting anything down or, creating a huge safety hazard. All right, so the senses are collecting all these raw numbers. Now let's talk about the brain and its job of turning that raw data into something actually useful, something smart. So the ESP32 microcontroller, our brain, it's like the central command hub. Its first job is to basically have a conversation with all 3 of the energy sensors. It uses this special language called Modbus to ask them for the readings. And that's how it gathers all those raw measurements, the voltage, the current, the power, from every single phase. But honestly, collecting data isn't even its most important job. No, its most critical job is safety. Look, data is great, but this little brain is constantly on guard, checking for any dangerous conditions to protect not just the equipment, but the entire building. And we're not talking about vague rules here. The source code lays out the exact tripwires, and they're programmed right into the device. It's watching for overvoltage above 260 volts or undervoltage below 180. If the current spikes past 100 amps or the total power surges over 22,000 watts, it sounds an alert. That's real onboard intelligence at work. Okay, so the brain has done its job. Next up, the network. How do we get all this amazing data out of the lab and into the wider world? Well, this data's journey is nonstop. Every 15 seconds, just like clockwork, the ESP32 packages up all the latest readings and zips them over Wi-Fi straight to the cloud. It's such a clean, powerful flow, from the wire to the brain and out to the web. And get this, it doesn't just go to one single destination. This is where the whole Internet of Things idea really shines. The data gets broadcast to a whole universe of different platforms at the same time. You've got ThinkSpeak and Google Sheets for storage and logging. You've got Grafana and Tableau to create those beautiful dashboards. And then you've got other services that can build a public website or even send you an email alert if something's wrong. It's incredibly flexible. Which brings us to the grand finale, the vision. This is the payoff. This is where we take all that raw, complex data and turn it into something genuinely insightful, something we can actually understand. So let's take a step back and look at the whole shebang. This is the complete, end-to-end architecture of the entire system. It shows the whole journey, right? From the physical sensors clipped onto wires in the building, up into the cloud, and then all the way back down to the amazing charts and graphs that pop up on your screen.
And hey, this isn't just some abstract drawing on a slide. Check this out. This is a real early prototype in action. You can see all the hardware wired up, ready to go. And the best part? You can see the data streaming in live on that little LCD screen and on a smartphone. This is that magic moment where it all comes to life.
And the end result of all this hard work? Clear, live, absolutely beautiful charts. I mean, this is what it's all about, isn't it? Taking this super complex, totally invisible electrical data and turning it into something simple, something actionable that anyone can look at and just get. And this system is no slouch either. It's robust. Just in its initial run, it successfully logged and analyzed over 8,000 data points. That right there proves it's more than capable of doing this job long-term, around the clock. When you boil it all down, this whole project really proves one powerful idea. The true power of modern IoT is its incredible ability to take something invisible and make it visible. And that really leaves us with one last big question to think about. Now that we have the power to actually see our energy use this clearly, what's the very first thing we should change?